加100块钱换了一个无线的，然后卖掉，然后卖了1000，卖了1500。
你说国内1500，这也不错，
相当于基本上是一个300刀。但是它键帽很大，它的键帽很大。我觉得用什么都是用习惯了。是吗？
所以我想换个电脑。
我之所以买这个电脑，就是因为出来问作业，你拿问题别人都说跟你用的不一样，还要去比较麻烦，所以我是买一样的，这样请教问题比较容易。不知道为什么我们现在小孩越来越多。
这个东西接外设是吧？就是
它只有一个 USB。
那个Surface 也
拓展，
而且只有一个
那个拓展。
其实有的一个。
我有一个。
Okay, 2 o'clock. We should start.
没有我的也需要拓展啊，因为我的也很小。
I hope you guys have seen that homework 1 is on the website. And I've been told that this is kind of a lengthy homework, so you should start yesterday, if possible. And if you have questions or anything, just shoot a message on the discussion board or come to all our office hours, any of our office hours. Any questions about the homework? Has anyone seen it yet? Yes.
I actually have a quick question. On one of the problems, it asks to test the accuracy of the decision trees we're making. Is that just, you want that to be a percentage? How are you looking for us to define accuracy?
I don't care, a percentage, a fraction, anything. Let's say percentage.
Okay.
What fraction of your predictions are correct?
Thank you.
So one of the problems talks about the Gini coefficient.
Yes.
Is that on the inputs or the outputs or both?
So,
because it's like P times 1 minus P.
Right.
I'm just trying to understand.
So let's think about entropy. Let's think about entropy. You calculate the entropy using what? Some probabilities, right? What are the probabilities there? Which probabilities do you use to calculate the entropy? It's the outputs.
Yeah.
And you're just replacing entropy with the Gini coefficient or the other one, the misclassification rate. So in all cases, it's the impurity, quote unquote, of the label that matters.
So if there's only 2 classifications, it would just be like 70% times 30% would be your Gini coefficient.
Or something like that. Yeah, whatever the number is. I don't remember that. Yeah. I saw, okay.
I calculated the Gini coefficient and tried to compute the information number, and is it possible for it to be negative, or is that something that right away should be applied?
So you should, the probability of each thing should be a number between 0 and 1, right?
Alright.
So that should answer your question.
So those things are interpreted as probabilities?
No, P times 1 minus P. P is a probability.
Okay.
So the Gini coefficient is sum over all I, whatever the label of Pi times 1 minus Pi.
Yeah, but the Gini coefficient itself was not negative. It was like the information number where you...
Yes, there is a negative, the entropy has negative P log P.
Okay, so it is possible for it to be negative.
No, it cannot.
Oh, something weird happened then.
You had a question.
In the homework decision tree problem, there is a missing value, the non-value. So when we calculate the entropy, should we pretend a value for that? Or
Which one is a missing value? Are you talking about the experiment or the...
It's a non-value in the decision tree.
No. Are you talking about the experiment or...
Which experiment?
Experiment. Do you remember, Srikumar?
Missing value? I don't think there's...
Okay, send an email, we'll figure this out.
Okay.
There was another question somewhere here. Yes.
The base of the logarithm is... yeah, but why?
Why? Because... Here's a good question. Does it matter?
You get a different answer. Does it depend on the number of outputs, like the type of function you're mapping to?
No, but will you really get a different answer?
If you, I mean, you can convert it to the base 2 and then you
But-
get a number.
Will you get a different answer? What is the answer here?
The answer is the amount of entropy.
Yes, but what do you do then?
Compare.
Compare.
Yeah.
Will the comparison change? Will the ordering of the attributes change?
The ordering won't change.
So,
But it won't be a number between, it won't be like 90%, it won't be 90%.
it's not a percentage, right?
Yeah.
It's not a percentage anyway, so
Okay.
it doesn't matter.
Okay, yeah, you're.
The reason log to the base 2 is used is because it has connections to information theory, and there are historical reasons, but it's all basically just a scale, right?
The slide specifically says that it's describing binary for entropy. The algorithm is, or the formula is for binary classification. How does it differ if you had more than 2 labels?
Oh, it's the same. So in fact, one of the slide right after that talks about entropy for multiple classes.
Okay.
You sum over all labels, pi log pi. It's basically the same.
Okay, that's what I figured. I just wanted to make
Yes.
sure. Okay.
And in fact, the definition of entropy also extends to continuous random variables, where you, instead of the summation, you make it an integral. So the same idea holds. You sum over all outcomes effectively. Other questions about homeworks? So good, at least 8 of you have seen the homework. I'm happy. Another announcement is, yes, a reminder. Yes?
Can misclassification rate negative?
Can misclassification, so this is from the remote audience. The question is, can misclassification rate be negative? The answer is, let's think about the definition of misclassification rate. The misclassification rate is what would be the accuracy of the classifier if you pick the majority class. So the accuracy is a number between 0 and 1, so it cannot be negative. It's a fraction. How many, or actually what would be the error? What would the error be if you pick the majority label? And the error cannot be negative. So the answer is no. Other questions? Right, so this is another announcement about projects. Just a reminder, I spoke about this in the previous class as well. Please start thinking about who you want to do your project with. You can either do it by yourself or with someone else. In the past, I was insistent that it should be with someone else because that will give you an excuse, any excuse to get computer scientists talking to each other. But there are often very good reasons to do your project by yourself. So in either case, let me know. Let me know by email. Some of you actually told me in person, but I just want to remind you to send me an email. Send me an email about your project team, and you have to tell me by 15th, I think, the date's on the website. In fact, your projects have a bunch of milestones. You have to first tell me about your project team, and then eventually, after a while, tell me write a one-page project proposal where you'll tell me what your project is and why you think I should find it interesting. Somewhere in the middle of the semester, you have to send me an intermediate report just to inform me about what's the progress and stuff like that. And then there'll be a final report. Each of these milestones carries some portion of the project grade, and there's information about this on the website. Please read the project page. In particular, if you're wondering what kinds of projects are kosher, typically there are 4 or 5 kinds of projects. The most common one is you pick an application and you basically implement a machine learning solution using something that you've learned in class. It could be something like you want to predict whether the price of milk will go up or down tomorrow, and somehow you found some data, or you found some data on Kaggle or something. Another class of projects could be you read a paper that uses some machine learning somewhere and you want to implement it and try to replicate the results. That's also somewhat frequent. Another group of projects is if you're already working on something, either in your job or part of your own research, and you want to take a fresh look at it through the lens of machine learning, go for it. That will be very interesting. The less frequent but often more difficult and more interesting project is something theoretical. Either you can try to prove some theory, some statement about learnability of some classes or functions using some assumptions about the learning protocol or something. This is very rare. I mean, last year out of probably about 70 projects, we had maybe 2 of these kind. Another kind is where you invent your own learning algorithm, and that's also somewhat rare, but if you convince me that there's something interesting going on, you have an interesting insight and you want to explore an idea, go for it. I'm not asking for necessarily original research or something publishable. All I'm asking for is an exploration of some ideas that take us beyond what you see in the lectures. Okay? Questions about projects? And I think all of this is probably somewhere in the website. There's a link called projects, and you might find more information. There are also some suggested project ideas that I don't know, I just thought of someday. If you ask me what they are, I'll have no idea, but take a look, and if you want, tell me if you want to work on anything. Yes?
Maybe you have to submit one shell script which we can run to check the programming assignment.
Right, so for the programming part of your assignment, it has to be a shell script, basically a run script file, which does whatever it is that you have to do. It might compile it, it might download something from the internet. There has to be one shell script inside a source directory. Maybe the source directory also contains the data. The TAs will run the shell script, and it has to reproduce the same results that are in your report. That does not mean that you have to basically have a bunch of print statements saying that prints the same numbers that are in your report. It has to actually build a tree or whatever. And if the shell script does not work, you will lose a certain fraction of the grade that's assigned to that part. And did you want to add something to that? Okay. Basically, make it easy for us to grade your work. Don't give us grief. And that's a generally good policy to have in life. Any questions about homeworks, exams, projects? What?
Perl.
Perl? Why don't you make it a shell script? Okay, we'll talk about this later.
You can bash script that just calls your Perl.
Exactly, you can just have a bash one-liner that calls your Perl.
If you want to use make, you can just have a bash script that just calls make.
There, that's your answer. And the thing is, the reason I'm not very okay, all of us at least kind of can run Perl script or Perl on the command line, but I don't want to make it a habit, because then the next thing would be you have some weird language that you want to use and nobody knows how to run it. We don't want to have to install a compiler. We'll only use the set of tools that are available on the CADE machines. And that reminds me, please try to log into CADE if you've never done before. You might get some, it's easy, but you just want to make sure that the whole pipeline is clear. Yes?
As a note, if you find that you want something installed on CADE machines and it's available on the repositories, you can email operators at aim.utah.edu and ask them to
You know what you should do? Send that to the discussion forum. Send that message to the discussion forum. That's very useful. Thanks. Okay, I think I'm sure you're not here to listen about logistics. Let's get to the class. And we're going to continue where we left off. And that was the nearest neighbors algorithm. And in the last lecture, we started looking at the k nearest neighbors algorithm. And this is a very, very simple learning algorithm. Calling it a learning algorithm is a bit of a stretch, because all that's needed is to read the data and store it in some format that is easy to access. So that is learning, and prediction is just literally going over the entire training data, finding the k points that are closest to your test example, and picking the majority label. And in practice, as I said towards the end of the last lecture, it's good to use an odd k because you're looking for majority, and if you have two nearest neighbors and if both the neighbors are basically equally far or have different labels, then you can't break ties. To use k nearest neighbors, you have to, or to find k, you need to use some sort of a cross-validation scheme, and you will be implementing that in your homework, and I'll be talking about cross-validation in a bit. One point about k nearest neighbors, and this is something that we'll get to a bit later as well. So remember that the most important, pretty much the only knob that you have in the k nearest neighbors is the definition of the distance function. How do you measure distances between points? So very often in practice it becomes really important to normalize your the example so that they are all unit vectors or something like that, so that your distances are not dominated by some one feature. And this is, and there will be an example at some point that will force you to work through this idea. And there are many variants of this. So, any questions about the mechanics of the k nearest neighbors algorithm?
I mean, in a nutshell, isn't it pretty much just running through each of the inputs and checking which one's got the shortest distance? Or which the k...
Yes. Basically that's it. You find the k points that are closest and they vote on the new point. And that's about it. Let me do a quick detour because I talked about cross-validation and you will be doing cross-validation in the homework. I'm going to do a very brief detour on cross-validation. And this is really important because this does not just apply to k nearest neighbors. This is a general skill that you will learn that applies to every machine learning experiment that you will run. The idea is the following. You want to train a classifier. It could be k nearest neighbors, it could be support vector machines, it could be something. And typically these learning algorithms require some hyperparameters, some inputs that you give to the program. Like for k nearest neighbors, before you even start, before you even do the whole thing, you have to decide what k is. How do you know what's a good k? And these kinds of inputs to the program or to the learning algorithm are called hyperparameters. And the choice of the hyperparameters is often really important because what we need to be careful while choosing hyperparameters because we should not find hyperparameters that best classify the test set because that's cheating. So we need to we only have the training data because effectively looking at the test set to find hyperparameters is like getting a peek into the future because test examples represent future data points that we don't have access to. So in practice, the only thing we can do is somehow use the training set to find both the best classifier and the best hyperparameters. And one way to answer that question is this idea called cross-validation. Now, I'm going to give you a very brief run-through of cross-validation, partly because you are going to implement it in your homework, and we'll come back to this idea in a later lecture when we talk about model selection. The general setup is called k-fold cross-validation, and here k is a different k from the k nearest neighbors because we're not very creative with our choice of numbers or choice of variable names. So we use k-fold cross-validation. What we do is say you have a training data, your training set consisting of multiple examples. You split it into k parts. In this picture, I have split the data set into 5 parts. And you pick 4 of them, pretend that that's all the training data that you have. You train your classifier using a particular hyperparameter, one particular choice of k for k nearest neighbors, for example. And you evaluate that on this held out data set called the validation set. You find some accuracy. I have called it accuracy 5, which is Just saying that this is accuracy on part 5, on fold 5. You do this for all possible cases. You pick 4 folds, 4 parts, train, and evaluate on the held out data. So you get 5 accuracies. Remember that in all these 5 cases, or k cases, you use the same hyperparameter. What you do next is you find the average accuracy across these 5 things. Just, we know how to find averages. And this performance, note that we have not used any test set, we have just used the training set, and we have some measure of future performance in expectation for a particular choice of hyperparameter. Now, this is the quality of your that particular choice of hyperparameter. Let's say you want to try in your homework, for example, I'm asking you to try k equals 1, 2, 3, 4, 5. You repeat this for all possible values of k, for the k nearest neighbors, and then you find 5 values of this average accuracy, and now you have for every value of k for k nearest neighbors, you have one number. What do you do next? That number corresponds to the quality of that k, right?
So pick the one with the best performance.
Exactly. Pick the one that has the highest average accuracy. It's called the highest cross-validation accuracy. And now you retrain your classifier on the entire data. So now you have a particular value of k for k nearest neighbors, and you retrain your classifier on the entire data using that particular value of k. You should get into the habit of using cross-validation irrespective of where you use a learning algorithm to pick hyperparameters. Not just for the class, but I'm sure many of you are in this class because you want to learn about machine learning to, beyond just the fact that you get 3 credits. And if you are going to implement any learning algorithm, typically there's always a decision about hyperparameters, and one of the best ways of picking the hyperparameter is to use this procedure called cross-validation. You can do this computationally. There are lots of tricks that you can use to make this faster, because every fold, each of those slices can be done in parallel and such things. So there are a lot of tricks, but the vanilla version is very simple. It's just literally split the data into k parts, train on k minus 1, test on 1, repeat this for all possible choices of k minus 1, take the average. And do this for every choice of hyperparameter value. Question?
Are we sort of doing like a machine learning algorithm for when we do cross elements?
Actually, that's an interesting question.
Is that kind of a form of learning
That's an interesting question, because cross-validation historically comes from the statistics community, and what you need to keep in mind is typically there are very small number of hyperparameters, maybe 1 or 2 numbers. So you can literally just do grid search, which is you have a handful of options, you try each one. The learning algorithms that we will see are not amenable to that, because you may have 1 million parameters. You cannot try every possible value for every possible parameter. So that's another sort of sanity check. If you have too many hyperparameters, then there's something funny going on, because you're doing grid search, then you're actually literally just learning. Yes. You.
So what is accuracy for one set is bad, and for other 4 is good? The average do not reflect that.
That's fine, because it's an unbiased estimator of the future performance. So yes, it's possible that for some choices of your training data, your performance will be bad. So then that value of k is, or whatever the hyperparameter, is lousy or has to be penalized.
So when you're averaging in a balanced way, you're actually implying that the training set, all training sets are always the same.
Yes, there's an implicit assumption here that there is all the training examples are independently selected and are identically drawn from the underlying distribution.
So is that always true?
That's a strong assumption that we always make. This assumption of IID, and we'll talk about that when we come to learning theory a bit more. But yes, that's a good observation.
But actually, can you actually say that it's not always true and give some weights based on how correlated they are in the training set?
How do we know that? problem is, how do we know that? Unless you have some domain knowledge that already gives you the answer. Yes?
I remember it was when we were talking about trees, there was the test set, then some second set that we were using to...
The validation set.
Yeah, validation set.
So the fifth part here is a validation set. That's the name, that's the origin of this name. It's cross-validation. You do validation multiple times.
So it's basically a generalized version.
It's not a generalized version, it's a way of avoiding bias by saying that there's this one validation set that has some weird properties, so you're averaging it out across multiple ones. Yes?
So is this ever used for decision trees and choosing the root node?
No. Choosing the root node is basically part of the learning algorithm.
Okay.
Where it's used in decision trees would be to say that, say you have, instead of growing the full tree, you're going to put a depth limit. The tree should be no longer than, I don't know, 3 deep or 18 deep.
Okay.
How do you know what that number is? The choice of the root node is part of the learning.
Okay.
The fifth number you had there, it was a validation test, and it's also used in the training set for the next validation
In
set?
all the others. So notice that actually that's also an interesting observation. Part 5 is part of the training set for all the others. So I'm going to try to use the pen again today, and someone sent me an email on how to get rid of that bottom bar. Let's see if it's correct. So part 5 here is the test set for this first row, and for all others it's part of the training. What that means is every training example is part of some test set. Right?
And the number that we choose to split on, how does that
Which
factor
one?
in? The 5 or 10, you say K is...
Yeah, you know, in the extreme it can just be, the extreme version of this is called leave one out cross-validation, where you train on all but one examples and test on one. And you do that, now the number of trials that you run is the size of the training data. That's a bit extreme because you have to run so many experiments. So often it becomes a matter of convenience. Leave one out cross-validation has some very good computational properties for linear regression, but in general not necessarily.
So it becomes a heuristic on itself.
There are some
another hyperparameter.
There are some guarantees with respect to cross-validation. Typically, I can tell you in the large applications that I've been involved in, you pick K equals 3 or 5 and just run with it. It does not matter so much. Leave one out is a bit extreme. Not doing cross-validation is just not right. So you pick a reasonable number that works for you computationally. Okay, and if you have trouble with this, don't worry, you will be implementing this, so you will have another opportunity to actually learn it by doing. And you know, office hours and all that stuff. So let's get back, so that's the end of the detour. Let's get back to where we were. We're still in the K nearest neighbors lecture. And, oh look, this thing has appeared.
I'm just curious, those detour slides, are they up on the website as well?
No, they should be there. So in general, the slides, I tend to update them up to the beginning of the class, and I'll post the latest after class.
Thank you.
So, looks like the best way is just to end the presentation and start again. Anyway, so we are still in the K nearest neighbor lecture. We are now going to talk about the actual function that the K nearest neighbor classifier is going to learn. And the answer to that question of what is the hypothesis space is something called a Voronoi diagram or a Voronoi cell. Some of you may have seen Voronoi cells before in, if you've taken robotics or such things. I'm not going to do a very formal introduction. I'm going to give you sort of a land wavy version of the story, and you will be playing with it yourself also in the homework. Just a reminder, a decision boundary is, okay, so even before that, the goal of learning is to find an approximation of some function. There's a hidden function and we want to find an approximation. And what I told you before is that learning is really search over functions, right? I also told you at some point, maybe in the first lecture, that learning is also the same as, or the goal of learning is generalization. And in your own spare time, I want you to reconcile these two versions of the story. And one way of visualizing a classifier is to use this idea called a decision boundary. A decision boundary is simply the line or the plane or in general the surface, does not have to be linear, in general some surface that separates points that belong to different classes. And equivalently, another way of thinking about this is every point in the space of examples can be classified. Which points will be classified as positive and which one will be negative, and the region, which region of the space is positive and which is negative, and the surface that separates these two is the decision boundary. And I want you to remember that we've already seen an example of decision boundaries in the context of decision trees. When we had real valued features, if you remember, we created these splits or these thresholds which we used as tests, something like this. And based on these tests, any random point, any point on the two-dimensional plane can be assigned a label plus or minus. And it just so happens that in this particular tree, the decision boundaries are not linear. They are this blue line here. They don't have to be linear, right? But I want you to convince yourself also that if you only have thresholds of this kind, greater than 3 or less than 7 or something, you will get axis parallel boundaries. Lines like this, you will never get something like this. If you have thresholds of this kind, because you're only using one feature. And it's not a very difficult thing. I just want you to stare at it for a few seconds, you'll see the point. But that's not the goal of this lecture. The question is, what is the decision boundary for the nearest neighbors algorithm? The nearest neighbors, just learning involves literally just remembering all the training data. And prediction is to find for example, if you have k equals 1, you find the nearest point and predict the label as the label of that point. Then what is the decision boundary? Or in particular, are you ever explicitly building a function? Are we learning a function for k nearest neighbors?
We're learning the Voronoi diagram.
Yes, but are we learning actually a function from x to y? Not explicitly, because we don't ever store a hypothesis as a function. We store the hypothesis as just a set of instances as defined by the set of training instances. But that doesn't mean that there is no function. We can still ask, what is the implicit function that's being learned? And the answer to that is the Voronoi diagram. And I'm going to illustrate the idea of a Voronoi diagram using this sort of a cartoon example. Say you have a bunch of points in the space. In this case, it's just two-dimensional. For any point in the space, let's pick this point here as an example. All points that are closer to this point, so let's say this point, the red point is closer to this one than anything else. So it belongs to the Voronoi cell of, let's call this point A. Every point in the space, for one nearest neighbors, has a nearest training example. And the set of all points that are closer to this point A than anything else constitute what is called the Voronoi cell of that point. So basically, and this, the Voronoi diagram is simply the union of all the Voronoi cells. So, for example, for these collection of points, every point inside this polygon is closer to this point here than anything else. So, this is the Voronoi cell for the center point. And you can do this for all the points here. Okay? Given a finite set of examples, we can always find a collection of Voronoi cells. And notice that the other important point is that some of these points are, labeled positive, some of them are labeled negative. In this case, I have used red and blue. You have blue points here and red points on top. By definition, the one nearest neighbor classifier says that any point that's say here is closer to this one than anything else. So when you pick the nearest neighbor, you'll pick the representative point that created that Voronoi cell. What that means is all points inside this region will be colored red. So the function that the k nearest neighbors or the one nearest neighbor algorithm is learning is the following. You take the training data, find all its Voronoi cells, and color each cell by the label of the point that created that cell. This can potentially give us very complicated functions, because here the decision boundary is something like this, right? So this is one answer to the question of what is the hypothesis space, or what is the function that the one nearest neighbor algorithm is learning. It's also true for k nearest neighbors. By the way, I drew this picture using, first of all, this is only a cartoon. It's not mathematically accurate. Don't hold me up to this. But the intuition I've used here is to use the Euclidean distance or the L2 distance, and the Voronoi diagram will change depending on the distance function that you use. This is for one nearest neighbors. When you go for k nearest neighbors, as k increases, there are also partitions points, because basically any point that you get, you can find k nearest neighbors and find some sort of a label, and that label will become the color of that point. It's harder to draw, so let's not worry about that right now. Are there any questions? Yes.
So you're saying that this way of partitioning the space describes a family of functions that follows this Voronoi cell concept. But we could partition it instead of, say, ellipses, and partition the space that way. Or is it because this can fill every spot?
Aha. If you use, let's pretend that you use ellipses. Let's go back to this data here, and let's take ellipses. Let's say or circles, or some version of that I'm going to draw right now. So this is one, something like that. First of all, there's the point that you raised. Every point in the space is not covered, right? The second thing is, let's pick a point that is not covered. Let me also pick another color just to. Let's pick this point here. Okay? That point is not in any ellipse, but you can still run the prediction, right? How do you do prediction for one nearest neighbors?
The closest.
You pick the closest point. So you pick one of the closest points. I don't know. Let's say it's this one here. Which means, even though you've not, built this idea of an ellipse, you've not included this in any ellipse, it has a label. So now your ellipse should get bigger.
Yeah, it's a new ellipse. Yeah.
I can keep doing that till you get these edges. Now it's possible to prove that the boundaries of these cells have to be linear. And objects that we get with these kinds of linear boundaries are these collection of polygons. They form the Voronoi cells. Yes.
So apparently we could, instead of storing all the data, we could store the generated Voronoi set instead. But sometimes that might actually be bigger.
Possibly.
Than the input data, right?
Possibly. There are multiple implementation details that I'm kind of just skimming over that you could possibly implement to make your prediction more efficient. Because if you have n training examples, the time complexity of prediction is n. And we live in the world of big data, so n is large. So you want to, you're right, I mean if you can find ways of making that better, but then you have to figure out how to actually find the Voronoi for an arbitrary distance function in n dimensions. So,
Not easy.
maybe. Yes?
Is distance always a function of 2 points, or it can be a function of more than?
In this case, I'm defining it as a function. Distance is generally a function of 2 points.
I mean, for example, is density of the region that you want to have any impact on the output of the?
What do you mean by density?
Like, you know,
How many points are there in that space?
Yeah.
That's a different algorithm. Potentially, you could use that to weight the labels, to weight the vote that each point gets. Right? So, there are tons of variants of nearest neighbors. So, this is the one version that I presented here is the vanilla one, and you can have weighted versions, you can have some other normalized versions. What you are describing is basically a different definition of a distance function, where the distance is possibly, yeah, you could play with that distance definition if you believe that your data, your problem requires that.
I was just going to make a point about the ellipses. So it seems like, so the Voronoi diagram is really just it's an approximation of the true classifier that
Yes.
we're after. And so you could, like if you had tons and tons of examples, like these polygons could slowly start to approach what look like.
Yes. In fact, there's a theorem for nearest neighbors that says if you have infinite data, this will become the true function. Which is actually a very cool theorem, given that it's such a trivially simple algorithm to state. But yes, and that's because of what you just said. Okay, last question.
Sorry, this might be a dumb question, but how do you go about finding the boundaries to all these without having to plug in every single point to test the distance?
Which distance? What do you mean?
Just the boundaries.
Oh, this is the implicit function that's learned. You're not necessarily going to have all these boundaries.
Okay.
Given a new test point, you're not going to care about the other boundaries. You're just going to find distances to all the training examples.
Okay, so when drawing this diagram,
there are ways of computing the Voronoi map, and we won't be discussing those for now.
Okay.
So, as an exercise, I want you to take this very, very simple case where you have only 2 training points, one positive and one negative. And what would the decision boundary be?
A line. A line.
A line? What about it?
A line between the distant points.
The perpendicular bisector. Just the line that goes through this point. And this you should be able to prove. Basically, how do you prove this? How do you convince me that this is the right answer?
Actually, we can combine as the positive, like we can combine model as they have two electrons. So,
okay, there's some physical analogy there.
By nature.
By nature. By nature is an argument that's always right and yet, leaves something to be desired.
Just pick a random point x, y, and put
Yes.
the distances equal.
Yes. So the one property of the decision boundary is any point on the decision boundary is equidistant. So here's another question. If a new test point comes in and it lies on the decision boundary, how do you classify it? One answer was, somebody said flip a coin. Flip a coin. Another answer. Actually, that's the answer. You flip a coin because that's all you know. You're on the boundary, there's no other information that you have to pick a side. Okay, so that's pretty much all I have to say about Voronoi diagrams. But if you're feeling that you need to know more about this and stuff, don't worry, there's a question about this in your homework. So I'm sure there's enough to entertain you. And maybe it shows up in the exam, right? So let's get back to the rest of the lecture. We were talking about k-nearest neighbors, and I pointed out that the nearest neighbor algorithm is very easy, it has all these fun properties, and the decision boundaries of Voronoi diagram. Let's now move on to this other, another concept that is broadly applicable to all of machine learning, and it's kind of easy to introduce this in the context of nearest neighbors, and this is the idea called curves of dimensionality. So let me just, there you go. So to introduce this point, first we have to start thinking about why would a classifier ever go wrong? Why would your learning algorithm produce a classifier that might be incorrect on future examples? We've already seen a reason for this. One reason could be you are overfitting the training set. You are able to explain the training set so well that you are even explaining the noise in the training data. Always possible. Another reason is something called the curse of dimensionality. We will see multiple reasons. They're all related, but this is another concept that you have to know when you're getting through this class. And the curse of dimensionality is, intuitively, the idea is that the notions that you bring to the any intuitive ideas that you may have with 2 or 3 dimensions through 2 or 3 dimensional spaces do not necessarily generalize when you move to higher dimensional spaces. So at this point, some of you, I'm sure, are slightly getting uncomfortable about the idea of a higher dimensional space, and I don't know who it is, but you did.
What? I didn't do anything.
You didn't do anything?
I just have a question.
Yes.
When you say that the methods don't work, does that mean that they are not accurate, or does that
No,
mean
it's not that. Your intuitions should not be used to guide. And I'll give you some examples. And so what I thought you did, that's the other thing I wanted to mention. One of my goals for the end of the semester is to try to know all your names. At this point, I know like 2 and 3, let's say, if I include all my TAs. So I don't know who sent me an email to point me to this really cool book, 1884 book.
That was me.
Thank you. It's actually a fun book called Flatland, A Romance of Many Dimensions, and it's a very cute introduction to the idea of the 4th dimension. If you are feeling a little uncomfortable about n-dimensional spaces, I would strongly recommend that you read this book. It's small, it's entertaining, and it's free. It's on Gutenberg, and it's older than all of us. So anyway, getting back to the point. The examples that we have are n-dimensional points. And we want to measure distances. When we are talking about k-nearest neighbors, we want to measure distances between points in n-dimensional spaces. And if you notice, all the examples I had were basically projections on this 2-dimensional slide, and at some points I just wave my hands around to talk about distances in 3 dimensions. But sometimes adding more features can be a dangerous thing. Why?
It can help you take something that was beforehand not classifiable and make it classifiable.
That's a positive, right? Mm-hmm. What might be a problem?
All I was going to say is that sometimes a property that holds in a 2-dimensional space no longer holds. Like, for example, a random walk in a 1 or 2-dimensional space does eventually return to the origin, but in 3 or more, it
Yes.
goes away. So it just, certain properties just don't hold anymore.
Yes, that's basically the end of this lecture, but yes. There's another very, very easy answer for why adding new features might not help you.
You could end up adding noise.
You could end up adding bad features. Very, just a simple example. I have a name classifier, the one that we saw earlier in the one of the previous lectures. I want to classify names, and I'm going to add a feature that says what is the length of this name, and then I'm going to add another feature that says what is the date of birth of this person who bears this name, and basically just random things. And as you keep adding more and more noise, the noise will overwhelm the actual signal when you compute distances, and possibly your classifier might need tons of data to actually learn. But that is an aside, really. Irrelevant features will hurt, most likely. And if you have, say for example, if you have 1000 features and only 10 of them are relevant, the 990 that are irrelevant will end up dominating distances, and so you are basically classifying the noise. The problem though is, let's pretend that all our features are relevant. Of these 1000 dimensional examples, every one of them is important to classify as a point. The problem we have is that even if every feature is relevant, in high dimensional spaces, as you pointed out, properties that we think are intuitive and true in low dimensions suddenly disappear. And I'm not going to give, there are many, many examples of this, and I'm going to give maybe 2 or 3 of those. And these are collectively, they come under this name of curse of dimensionality. By the way, the idea of this phrase, the curse of dimensionality, is was proposed, or that name is attributed to Bellman, and the same Bellman who invented dynamic programming, the same Bellman who invented the Bellman-Ford shortest path algorithm, and such things. So generally a smart guy. So let's just to illustrate this idea of the curse of dimensionality. Let's take this example. Say I have a cube. A cube in 3 dimensions is just a cube. A cube in 2 dimensions is a square. A cube in n dimensions is called a hypercube. In general, when we move to n dimensions, you add the name hyper. So you have hyperspheres, hyperplanes, and such things. So let's say we have a cube or a hypercube, and we try to fit a sphere or a hypersphere inside snugly. And we measure what fraction of points in the cube lie outside the sphere. So in this picture here, I can only draw in 2 dimensions. This picture here, I want to measure what fraction of points lie outside the circle but inside the square. In other words, it's the area of the blue region here, right?
Yeah.
So easy to do. So what's the area of the square? If instead of just jumping through the math, let's try to okay, this is going to take some time. Right, so the area of the square is simply 4r square. Yeah. And the area of the circle is right? This is the fraction we care about. And since we are grown-ups, we know how to do fractions, we can easily simplify this. And we get 1 minus pi by 4. Nothing fancy here. So the area of the region that's outside the circle but inside the square is pi by 4. That's the number of points in some sense, or that's the fraction of points that lie outside the, in this case, the sphere. Okay. Let's increase the dimensionality by 1. Let's go to a cube and put a ball inside. Same story, we can do a similar sort of calculation. We get 1 minus pi by 6. So in 2 dimensions we had 1 minus pi by 4, and now we move to 1 minus pi by 6. This number here has decreased. I'm not going to work out the math, but you can show that as the dimensionality increases, it becomes 1 minus some number here, and that number goes to 0. As the dimensionality increases, this fraction, the fraction of points that lie outside the sphere is 1 as the dimensionality becomes infinity. Now, leave aside the fact that I'm having trouble drawing on this, but let's think about this for a minute. We have a sphere, we have a cube, and we are fitting a sphere inside it. In 2 dimensions, there is most of the volume lies inside the circle, right? In 3 dimensions, it becomes a smaller number. It's 1 minus pi by 6, not 1 minus pi by 4, the volume that lies outside. But as the dimensionality increases, most of the volume lies outside. So basically, even though you're fitting a sphere inside the box, the sphere is empty. I don't know about you, but the first time I heard this, I was left deeply uncomfortable. Questions?
So this particular theory that the number eventually approaches 1 assumes the fact that we are dealing with only squares and cubes.
No, I'm just talking about this one particular example. I've made no other assumptions other than the fact that we're talking about squares and cubes.
Isn't it that the sphere doesn't become empty, but the sphere ends up having the same volume as the cube?
No, it's the volume of the cube minus the volume of the sphere is 1. And the volume of the cube is also 1. Which means the volume of the sphere approaches 0. Even though it snugly fits the cube. So most of the points, what this means, there a question?
Does that mean the sphere doesn't really exist?
Like, sphere exists. Because you can compute its volume, right? It exists, and yet there aren't enough points inside it. The problem is that at that point I cannot give a geometric explanation. This is algebra. The math says that this is what it is.
You can just explain it this way, that the volume of the hypercube will be much more in proportion to the volume of the. That's why it is approaching.
The volume of the hypersphere actually, yeah, sure, that's another way of doing it. In proportion, the volume of the hypersphere, but
much more.
But the thing is, we are only talking about unit cubes, right? It's not the absolute volume. We are not talking about fractions. Most of the points in high dimensions effectively lie far from the origin.
I was going to say that, like, yes, it's like the volume of the square is like basically completely dominates the volume of the sphere, such that it's basically the only volume. The interesting thing is if you were to try to sample the cube, you would never ever land inside the sphere.
Exactly. If you are going to randomly sample points from the cube with probability 1, you will get a point that lies outside the sphere as the dimensionality goes to infinity. If you randomly pick a point, most likely that point is outside the sphere, which is just bizarre. Let's take another example just to make this discomfort more clear. Let's take circles this time. Circles and spheres and hyperspheres. And what I'm going to do now is I'm going to take a sphere and pick an epsilon, a tiny epsilon, and try to fit another sphere whose radius, let's take a circle or sphere of radius 1 and another ball whose radius is 1 minus epsilon and fit it in. And now I'm going to ask, what fraction of the outer sphere lies outside the inner sphere? In 2 dimensions, it's very easy to draw. I'm going to put a circle inside another, and this length here, the length of the thickness of this ring is epsilon. some tiny epsilon, and I'm asking what is the area of this epsilon ring. And let's assume this is a unit circle. So what fraction of the area lies outside? It's elementary geometry. It's pi r square minus pi r prime square, whatever, blah blah blah. It is 1 minus epsilon power 2. This at least should not shock anybody.
Yeah.
This should cause no discomfort. Right? Okay? Then the refrain is the same. Distances are just weird in high dimensions. So, if you increase the dimensionality, it turns out the area or the volume of that ring in d dimensions is this quantity here, 1 minus epsilon power d. Epsilon is some small number, so 1 minus epsilon is less than 0. That raised to the power d, as d increases, goes to 0. So again the same thing. The volume of that tiny sliver of a ring, or what was a tiny sliver in 2 dimensions, suddenly approaches 1. Most of the volume of a sphere lies on the surface in d dimensions.
Would this motivate moving beyond a spatial notion of distance to moving on to some other notion of distance that you call distance?
I thought you were going to go manifolds on me, but possible. The implications of this is that distances don't behave the same way, and even if you use some notion of a probabilistic distance, similar sorts of statements can be proved. Once you go to d dimensions, as d increases, all bets are off, or many bets are off, let's say. Most of the volume in this case, in both cases actually, lies farther away from the origin. That's the underlying point. And what this means is that you pick a random point from the circle or the sphere or the cube or whatever. You pick 2 random points. Chances are they're going to be really, really far away because they are going to lie on the surface. They're going to be as far away as they can if you just randomly draw points in high dimensional spaces. Questions?
Why does this happen?
Why does this happen? Because algebra. It happens because it. Yes. Another way of answering why it happens is to think about. The fact that we are uncomfortable about it, the fact that this seems odd, is because our notions of geometry are dominated by 2 and 3 dimensional intuitions. This is how geometry really behaves. It just so happens that we have a perverted view of geometry which is biased by our experience in 2 dimensions or 3 dimensions.
Are we talking about a fixed value of epsilon?
Let's say fixed value of epsilon. Yeah, if epsilon goes to 0, then you get these limits that are less obvious at that.
So, the way I understood what you said is the value of 1 minus epsilon will always lie less than 1, even if it's like 0.999
Yes.
less than 1. And since you go to a higher dimension, that will tend to a 0
Yes.
as such, right?
Yes. And that means the ratio goes to 1. So, at this point, I'm hoping all of you are feeling uncomfortable about high dimensional spaces. And hopefully it is for the right reasons, not because this went over your head. So let me just quickly summarize the curves of dimensionality. Most points in 2 or in d dimensions lie far away from the origin, which means And in contrast, in 2 or 3 dimensions, in some sense, most points lie close to the origin. What this means is, to actually get, let's say, a uniform sample of the space, of the feature space, you need more points, simply because there are more points. There is more space to fill. And this particularly hurts nearest neighbor classification, because the fundamental operation that we care about is a distance between points. And if distances behave abnormally, then how are we ever going to get a classifier? The other intuitive way of thinking about it is, we're talking about a k-nearest neighbor classifier, which means, what's the assumption that we have in k-nearest neighbors? The assumption is that for any labeled training point, some neighborhood around it has the same label. Right? There's some small neighborhood that lies around it that has the same neighborhood. That neighborhood is the Voronoi cell, but that's the assumption. But if this notion of neighborhood breaks down, if all points are basically just far away from each other, then there is no notion of a small neighborhood around a point. That's the problem that we have from the classification point of view. There are also computational problems, because if you have high dimensional spaces, as dimensionality increases, the number of ways in which you can slice and dice the space becomes much bigger. Think of how many squares, let's say you divide a unit square into every dimension of a unit square into three pieces. So you get 9 little squares, like the tic-tac-toe grid. If you are going to 3 dimensions, you do the same thing, you get 27. In d dimensions, you get 3 power d. It's just an exponential number of, in some sense, neighborhoods. So there are computational problems as well. So again, we are running into the same question, a similar sort of a question that I posed maybe last week, which is, things are not going to work in d dimensions. We need all those features, but even if every feature is relevant, all bets are off. How do we deal with it? Why do classifiers work? Why do nearest neighbors classifiers even work when distances are meaningless? Any thoughts?
They're still good enough for comparison, I guess?
Yes. Why? What could that mean? If the distances are still meaningful and yet they are not, in the worst case, we are host. But we don't seem to be, so what's going on?
Not the worst case.
We're not the worst case. And this suggests, and all of this slide is basically sort of more hand-wavy than the rest of the discussion about curves of dimensionality. It just seems that most real-world data is not uniformly distributed in the high-dimensional spaces. There are clumps of points that are close by. Points seem to lie on surfaces, on lower-dimensional structures inside this high-dimensional space. And there are different ways of discovering a low-dimensional structure of the data. And these come under dimensionality reduction methods. We'll get to this probably the very last lecture of this class for the semester. That's one answer. Points, even though they seem like they lie in a million-dimensional space, are actually just literally planes and lines, just low-dimensional objects. Another answer is that maybe the right thing to do, this puts extra burden on discovering good features. Because if I'm going to throw in all the features I can think of, I'm only hurting myself. So feature selection is an important problem. It's an important and extremely not easy problem. It's almost an art. It requires a lot of domain expertise. And how do you know what a good set of features is? Let's say you have 10 different sets of features for your problem. And let's say you want to classify, I don't know, what did I say as an example? Let's say you want to predict whether the price of milk is going to go up or down. And you've done some analysis of the economy, and you want to correlate it with oil prices and the day of the week and whatever. you have 20 different kinds of features, 20 different feature sets. How do you know what's a good one? How do you pick a good feature set? Something that's good enough, expressive enough, and yet does not kill you with high dimensionality.
Use cross.
How do you do that? And I heard an answer here.
Cross-validation.
You use cross-validation again. Do the same thing. You try different method, you try different feature sets, find which one has the highest cross-validation accuracy and use that. And in general, and this is just a general point, not just for nearest neighbors, but in general, any prior knowledge that you know about your problem typically helps. If you're trying to solve natural language processing, knowing linguistics doesn't hurt. If you're trying to solve computer vision, I don't know, thinking about geometry and knowing about colors and such things doesn't hurt. Questions about this general idea of high dimensional spaces, because of dimensionality, features and such things?
When you say that 2 points are likely to be really far away from each other, what do you mean exactly by that? Or that 2, maybe 3 points are basically the same distance away from each other because they're like infinitely away from each other?
They're not infinitely away. They lie on the surface. So let's try to build in the absence, I'm going to try to build some intuition. If I pick a random point from d-dimensional space, and let me tell you beforehand that all these points are within the unit circle, the unit sphere. You know by this theorem that with high probability that point lies on the surface. Let me pick another random point. I know that point also lies on the surface. Right? There is no interior point, even though I am allowed interior point. So if I want a little neighborhood around these things, where the label will be the same, that the set of points that are closest are all far away. They are all on the surface somewhere. Were there other questions? I heard some very active discussion. No? Yes.
Can you repeat why it's a bad news for the nearest neighborhood because of the dimension?
So that was what I was saying. So let's say that we have, let's say that we are picking, let's pretend, suppose that the points are drawn randomly, and let's say they are all normalized, so they all lie within the unit circle, within the unit sphere. Okay? And now, let's say I pick a point, a random point. The math that I did before shows that any random point, as the dimensionality increases, practically lies on the surface. Even though I'm allowed, even though the point is allowed to be inside, it lies on the surface. Now, let's say I pick another random point. It's going to lie on the surface. But if you have some data like this, if I get a point here, and the neighborhood around it is just this tiny bit. But if I'm going to pick points only from the surface, I can get points very far away. And then suddenly the distance between these 2 points becomes meaningless, because I care about points that are nearby. It's not going to be outside, but I care about points that are inside this region here. But I'm not going to get any samples because there are no points on the inside. Right? There are no points on the inside. I'm only getting points on the surface. So distances are naturally going to be at least as much as random points from the surface. The notion of a neighborhood is suddenly less meaningful.
Can we just regard the surface as a n-1 dimension?
Sure, but if n is going to infinity, n-1 is also going to infinity. And then you have to start doing the same analysis in the n-1 dimensional space. So eventually you will come to a point, but then it's clearly not true that all points only lie on a one-dimensional surface by reduction. So somewhere along the way things go wrong. Right? So let me quickly summarize this and also marvel at how much time has passed. So we looked at the nearest neighbors classifier, And this is by far the simplest learning algorithm that you're going to see. And yet it has such interesting discussion points. The one problem with nearest neighbors is that prediction is very expensive because you have to iterate over the entire training set. And that's where actually there's a lot of interesting computational tricks that can come into play. There are efficient data structures, in particular things called KD trees are very popular. And I think there is a significant overlap between this class and algorithms, and I also know that the algorithms class has been looking at hashing. So those of you who are in both classes will appreciate how hashing can be used to solve this problem. We can find approximate nearest neighbors by actually hashing example points so that distances are preserved. The one input to the nearest neighbor problem is the notion of a metric, some definition of a distance between points, and changing the definition of the distance might actually change the behavior of your classifier. And that is where you have the opportunity to actually introduce some domain knowledge. And we also looked at this question of what function does this classifier learn, and the answer is it implicitly learns the function that can be represented using this Voronoi cells. And the same, I drew the example in 2 dimensions, the same idea holds in higher dimensions. There are points, regions of space that are closer to one point than anything else, irrespective of what the dimensionality is. And finally, we looked at this problem of the curse of dimensionality. There's nothing we can do with it. We have to live with it. We live in an n-dimensional universe or something like that. And we just have to realize it, keep it in mind, and use it. Be aware that it exists. Question?
Is there any rule of thumb as to how many variables is too many, or is not enough?
The rule of thumb is as few features as possible, use as few features as the job gets done. In fact, we'll see learning algorithms that explicitly try to diminish the number of relevant features. And that, in some sense, that's an important point. This point of use only those features that are relevant, and part of learning could be just discovering which features are relevant. Possible. Other questions? Okay, now I have 4 minutes left, and my plan originally was to finish the curse of dimensionality in 20 minutes and spend 1 hour talking about linear classifiers.
You just made us so uncomfortable.
Well, I know, but at least I was entertained. I do want to actually, I like the idea of giving some exercises once in a while, just so that you get an idea of what's going on. I'm not going to give you the answer to these questions. Look them up on the class website and try to solve these. These will kind of just to and there are no grades or anything for this. It's just for your own entertainment. And in the interest of sanity, I'm not going to start linear classifiers right now. So I have 3 minutes. We can either ask me questions, or you can go. I see a half hand.
I was just thinking, so you mentioned that the Voronoi diagrams, this type of partitioning of a space, you can describe any function possible.
Sure.
And at the same time, the more features you get, eventually it's impossible to define anything.
No, there's still a function. The impossibility comes in from the learning point of view. You need infinite data to learn the function as the dimensionality increases, because any finite sample you have will occupy such a tiny part of the space. So the problem comes from the learning point of view. The function still exists. The function is a mathematical object that exists whether we observe it or not.
But it's impossible to learn.
It becomes harder to learn. Not that that stops anyone from trying, but Other questions?
consolidation, when you use it to check for dimensionality, and you take off a dimension or a feature, it's going to change the function.
Yes.
So the question is how much? I mean, is there metrics that measure like
accuracy? Remember that the only thing that matters in this game is accuracy. We don't care about how much you like a function, how much you like a learning algorithm or a feature. The only thing that matters is if it gets the job done. So we are searching now. Actually, that's an interesting point. You change the function, so you're changing the set of functions that you're searching on because you change the dimensionality. So yes, you're changing the hypothesis space effectively. Right. Okay, we should stop now. In the next lecture, I'm going to start talking about linear models, and probably that will carry on for a very long time.